Alright, in this video we'll take a look at BC Test 2008 number 6. And we're considering the logistic differential equation dy dx is equal to y over 8 times 6 minus y times the quantity 6 minus y. And we let f of t be the particular solution to this differential equation with the initial condition that f of 0 is equal to 8. And the first thing that we want to do is we have the slope field for this differential equation given below, and we want to sketch possible solution curves through the points 3, 2 and 0, 8. Well, what this illustrates is that a logistic differential equation has the basic form of two horizontal tangent lines with an S-shape curve between them. However, above the S-shaped curve is a curve that looks something like this, and below it is a curve that looks something like that. And I'll change the colors here just so that this will stand out. Alright, so the green lines are not really part of the graphs there. They're just the horizontal asymptotes. Now, the solution to a differential equation must be a continuous function. So those three different blue curves there are not all the same solution. They are different solutions given different initial conditions. So for example, if we started above the top horizontal asymptote, then the solution would be just that, sort of like that exponential curve coming down to the horizontal asymptote at the carrying capacity, which is the value of the upper horizontal asymptote. If we were in between the two asymptotes, then we would start at the bottom and we would work our way up to the carrying capacity, or to the upper horizontal asymptote. If we started below, then we would go down to negative infinity. And in real-world applications, what this means is that if you start anywhere in between the asymptotes, then your population will increase until it reaches the carrying capacity. So again, this line here would denote the carrying capacity. And the line below would be your initial population. So as long as we were starting anywhere in between the initial population, or 0, and the carrying capacity, we would the population would grow at the rate signified by that S curve there, and until it reaches the carrying capacity. Now, if we were to start with a population greater than the carrying capacity, then what would happen is that the population, part of the population, would die off until it reaches the carrying capacity, and it would be sustained at that point. If you start off below, that's basically starting off with negative population, which is not really something that can happen in a real-world application. So you're much less likely to see values, initial values that are below the 0 population level. But that's the whole crux, or the point of this particular question here. So it's saying if we began at 8,0, or 0,8 rather, which is above the carrying capacity, then what would the curve look like? Well, the curve would look something like this. It would pass through there, and it would come along and reach the carrying capacity. If instead we started at 3, 2, which is in between the two horizontal asymptotes, then we would start off growing like so, and of course our history would mean we were coming back from this direction here. So that's what the curves would look like if, or given, those different starting positions there, which are, for all intents and purposes, different initial populations. Alright, so that's it for part A. For part B, we want to use Euler's method with starting at t equals 0 with two steps of equal size to approximate f of 1. So with Euler's method, we begin with our x, our y, our delta x, our y prime, our y prime delta x, then our new x, and our new y. So we're given our initial condition is 0, 8. And we want to go from 0 to 1 in two steps of equal size, so our delta x must be a half there. Our y prime, which is y over 8 times the quantity 6 minus y, starting with y equals 8, is going to give us negative 2. And y prime delta x would be negative 1. That's our delta y. So now we're ready to construct the new x, which is x plus delta x, or 1/2. Our new y, which is y plus delta y, 8 plus negative 1, which is 7. So that will be our new starting point. And we go on to look at delta x, which is always 1/2. And our delta y now, which is 7/8 times 6 minus 7, which is negative 7/8. And our y prime delta x, just multiply those two together, we get negative 7/16. Our new x, x plus delta x, is 1. And our new y, which is 7 minus 7/16, or 6 and 9/16, would be our final answer to this particular question here, to question B. All right. Now the rest of this question on the AP test deals with sequences and series, and so that's not something that we are up to at the point of this particular question at this point in time. However, I do want to I will add a second video on the solution to the differential equation dy dt is equal to y over 8 times 6 minus y. And that's going to be solved using separation of variables and also partial fraction decomposition. So I will continue a second video with the solution to that, and we'll pick it up there.